Hello folks, and welcome back here to the workshop and to the second in our series on hacking the Tesla Model 3 rear drive unit inverter. For those of you that are new to this particular series, I would highly recommend that you go and watch the previous video because it'll explain of a bit more detail the approach that we're taking. So I'm not going to repeat myself on that. So as I say, have a look at the previous video for some more background. Now, what we've got for you today is, I guess you could call it the first milestone along the way, in that we now have control over the, I keep thinking of them as IGBTs, but they're in fact silicon carbide MOSFETs. So our MOSFET inverter power stage we now have control of. So that's what we're going to be discussing with you today. Not going to be terribly exciting, I'm afraid. We've got a few 12-volt light bulbs rigged up over there for your viewing pleasure. That's going to be about the height of the excitement. So let's talk a little bit about what we had to do in order to get all this system to work. And then I will give you a little bit of a demonstration and we'll talk about what's coming next. So I guess with a lot of this reverse engineering stuff, yeah, it's just perseverance with it, and it's the more time that you spend with a circuit or a system, the more of it that kind of starts to fall into place, and it can be little things at first, and then I kind of find that once you get through the first few roadblocks, the rest of them tend to fall away fairly quickly. So when we first looked at this inverter, and you'll have seen in the last video that what we had achieved was we had came along and we had tied down the reset pin of the Texas Instruments microcontroller here in order to put it into a permanent reset state. The idea there being that when it's in that reset state, all of its pins become inputs. It doesn't execute any code, and thus leaving us the hardware there for our controlling pleasure, as it were. So once we got that done, I keep calling them IGBTs, the MOSFET drivers, which are these guys here, so there are 6 of them, are STGAP1BS according to the part number on there. Now the 1AS is the closest thing that you can get a data sheet for, and the data sheet does seem to apply and the pins do seem to do the same function. So I guess it's just possible it's a special batch they made for Tesla. So we figure out the pin out. Look, we can kind of look up the data sheet and we kind of see that, okay, it's fairly simple. They have a shutdown pin, which you'll see that we've connected a wire here, just looking at this one in particular. And that shutdown pin needs to see a transition from low to high back to low again in order to enable the input stage of the driver, because these are of course isolated gate driver chips. And then there are 2 input pins, and you have to drive a 3.3 volt just on off signal in there to turn the relevant output stage of the gate driver on and off. That's all very straightforward. There's no trickery in there. And we got that part working, pretty quickly. But the problem was that when we look at the power stage here, there's no sign of the usual DC to DC converters that you typically see to provide isolated positive and negative drive voltage for the Mosfets, not IGBTs, Damien. Now, so okay, this is more of a volume product. It's, they don't want to be putting a bunch of discrete DC to DC converters in there. So we have a look and we see that there are some transformers on the board. There's two transformers. This one is T2 here, and this one here, I never even bothered to look at the designator. I think it's probably T1, is it? Possibly. But it's the bigger of the two transformers. Now, the next thing that I spotted and kind of threw me on a bit of a half-day dead end was that over here, beside the smaller transformer, we have a integrated circuit. It is U36, and U36 is a Viper 16A. Now, that was a bit of a surprise for me because I'd used those way back when for making little mains-derived power supplies. And they're basically the kind of a chip that you find in mobile phone chargers. Kind of cheap 5 volt, 12 volt plug top power supplies. I'm thinking, what are you doing, Elon? And then I figured, aha, he is deriving his isolated gate drive voltages from the high voltage DC rather than the 12 volt DC. And I connected up a variable high voltage power supply. I won't describe how I did that, it's a bit crude. To our high voltage rails with a pretty accurate milliammeter in series with it, along with a light bulb for current limiting, lest I screw up. And what was apparent was that once we got to about 65 to 70 volts, I could hear a very familiar kind of a sound of a switch mode power supply starting to start up. And the current was jumping up to about 20 to 25 milliamps at that voltage. Once it went up to about 90 volts, the kind of startup whine went away, and we settled down and started seeing a current draw from our high voltage that. So yeah, then we started to see the kind of typical switch mode power supply situation whereby as you increase the voltage, the current reduces. And to my pleasure, we saw the low side gate drivers get their voltage supplied. They got one side of it. They got a positive 18 volt supply. And I'm thinking, okay, great, so that's it. They're deriving their gate drive isolated supplies with a mobile phone charger control chip, a transformer, and feeding that into our power stage here. And that was great. I was even able to switch the low side transistors, and all this is great, but I've no sign of any power to the high side. And I did bunch of things, looking around, brought the voltage up to 400 volts on there in case it needed to see that to turn on or something silly. Nothing like that. And then I did a bunch of poking around on the circuit here, and I'm going to get rid of myself here for you now, and we will get rid of me, and we'll let you guys see the whole screen here. And I did a bunch of poking around. I found these, there's a set of these 3 transistors and an adjacent diode here. You can't really see the third one. I've got it buried under this little breakout board. But all of these diodes are connecting back to the high side power supply. And these transistors are connecting back then to this larger transformer. So then went ahead, and this is a standard TDK part. Went ahead and looked up a data sheet for that guy, and it turns out that it is actually designed for isolated gate drive power. And I think, okay, interesting. So is he doing something really crazy? Like, is he getting the low side power supplies from this transformer and the Viper chip, and then getting the high sides from the 12 volt line and this transformer here? And I'm kind of thinking, and I'm trying to figure out why that they would do that, and you know, I can't really see a reason for it. So then went along, had a look at the primary side, and the primary is driven by U34, which is another Mosfet. And there's a very obvious current sensing resistor in there. But there's no sign here on the top side of the board of any kind of a control chip to run this particular power supply. And then I start kind of thinking, oh no, Elon, don't do it. You know what I'm thinking? Is he driving this from the main microcontroller? And I'm saying, no, you wouldn't really want to do that. But are they doing it to save a few dimes? Then over on the forum, a guy had posted a picture of the backside of this PCB, because obviously I haven't removed the PCB here. To see what's on the back. Now there's not a lot on the back, there's a few components, but on the back here, almost directly under these caps and the Mosfet, is a little 8-pin chip, and there's a little 8-pin chip, and there's a, what do you call it, optocoupler, and a little discrete transistor on there. Now unfortunately the resolution of the picture is not great, but I kind of took an educated guess that what I was seeing here on the back was a power supply control chip, a feedback optocoupler, and a shutdown transistor that was being used by the micro here to enable and disable basically the drive for this transformer. And I'm thinking, bugger, you know, how am I going to find this? So then I started in on the micro here, and the musk-goo on the micro pins is not particularly strong. So I went in there and I just got like a little, just got a resistor like this, just whatever value, 100 ohms or something. And I started off tying one side of it to 3.3 volts and just running around the pins. And I put the scope on the gate of this Mosfet here. I put it on a slow scan so I'd be able to see if there was any glitching. And I'm flipping around the micro like this, and all of a sudden I see a little, boo, there's a little pulse on the scope, and I thought, aha. And I go pulse around, and there's a red LED here which is turned off at the minute. And I was noticing that as the power supply started up, this red LED went away. And then I found that if I went back and forth, particularly on this part of the micro, that the power supply stayed running. And I've got this lovely 262 kilohertz drive signal. And all of a sudden, my high and low side, both positive and negative gate drive voltages come up. And yay, I thought, okay, so there must be a pin somewhere here, some I/O pin, that if we pulse this is going to enable the little power supply driver chip in there. Well, it kind of turns out that I was wrong about that, as you know, tends to be the case with these situations. You end up kind of getting pulled down a bit of a blind alley. What was actually happening here was that because of the size of this, because of the size of that wire compared to the pitch of the pins on the main microcontroller, what I was actually doing was short-circuiting the VDD core supply to the VDD I/O supply. Now, the core supply on this device seems to be 1.2 volts and the I/O supply is 3.3. And this is the power supply control chip for the low voltages, the kind of logic functions. And it's, this thing is like, there's a 50-page data sheet for this thing. It's what it, all kinds of safety and protection features. And it was seeing the core supply rise above whatever threshold and was shutting itself down. Now, when it shut itself down, we lost all of the low voltage supplies on the board, with the exception of obviously the 12 volts that we have coming in here. And by losing all of those supplies, like the 1.2, the 3.3, the 5, and whatever else this thing makes, was removing the hold off for the driver chip that's underneath this transformer, and was letting the power supply run. And I think, geez, okay. I tried again probing around with a smaller probe to see if I could actually find the pin on the micro that was controlling this thing, but no luck. The only way that I could get the power supply to run was basically to shut down the low voltage supply with this device here. That would then bring up all of my isolated gate drive supplies, but then of course I had no low voltage supply to run any of the logic. And if I bring this chip back up, of course, as soon as those low voltage supplies come back, they trigger the shutdown mechanism, and then the isolated gate drive power supplies go away. So I went back to the photo of the rear of the board. I started trying to see exactly where that little transistor that I suspected of being the control element for the gate drive power supply chip was. I kind of narrowed it down, and there's two. I'm not going to really see them here. I don't have a very good zoom with this thing. It's just a cheap webcam. But there's two test points here right beside the transformer. One of them is TP106 and one of them is TP156. Now when I measure the voltage on TP156, we're seeing the normal 12 volts, 14 volts supply, but TP106 was slightly less than 3.3 volts. And I'm thinking, oh, okay, interesting. And that test point is almost directly above where that little SOT23 transistor is. I'm thinking, did you, Elon? Did you do it? Did you do it? So I got a resistor, I don't know, it's like 100 ohms or something, and put a probe to ground, tipped it onto that test point, and boom, away goes my 260 kilohertz. And now we have both our isolated gate drive supplies up and our 3 and 5 and 1.2s and all of our logic supplies up. So to enable the gate drive power on this inverter, we basically need to ground or connect a ground to test point TP106 right here. So once that is done, we see our 12 volt current rise up by about 200 milliamps, and all of the, as I say, all the plus and positive and negative, high and low side gate drive supplies come up. And I'm thinking, okay, that's interesting. So why do we seem to have two gate drive power supplies? And to be honest, I've no idea about that. I've got to do some more investigations on here. On a possibly interesting note, this whole Viper area here is not on the front drive unit logic board. So was this some kind of belt and braces thing that they put on there for the Now that I'm actually talking about it, now this could be complete nonsense because it's just popped into my head, but the rear drive unit has permanent magnets. And what if we were to lose the 12 volt supply to the inverter? What if we lost the 12 volt supply to the inverter when we're at speed? We get uncontrolled regen going on. So is this something whereby this is some kind of a backup gate drive power supply that kicks all the low side gates on? No idea. But we'll figure that out. So, all right. So basically, at this point now, to summarize, we have the main micro here being held in a reset state, pin 124. It's basically tied to ground. Don't mind this little breakout board here. I've just got this on here so that I can connect to, I can wire stuff up and test things, and that it's just a crude kind of a testing setup here. So what we've got here for you, I've got the analog discovery here connected up, and I've got it connected to all 6 of my gate driver drive pins. I've got the 3 shutdown pins, because what they do is the shutdown pin is connected to get together for the low and the high side of each phase. So SD bar is connected together on the low and the high for phase B, the low and the high for phase C, and the low and the high for phase A. So we have 3 shutdown pins brought back out here as well. So we've got 3 shutdown pins, 6 drive pins. Now, one of the interesting things we discovered here as well while testing is that with these ST gap, as I call them, I don't know what the correct pronunciation is, but with these gap driver chips, and the way they have connected them, it is now not possible to turn on a high and a low side on the same phase at the same time. So shorting out the DC bus is not possible even if we send drive signals to try to blow up the power stage. So that I was very pleased to see, because as you may recall, on both the large and the small drive units from the Model S and the Model X, you can tell it to turn on the high and the low, and it will faithfully do that for you and short circuit the DC bus. The Toyota inverters that I've worked on, if you try to do that, they just laugh and shut down. Whereas the Tesla inverters, if you do that, they say, "Sir, yes sir, turn on both the high and the low side," and boom goes your inverter. So sounds like Elon's been speaking some Japanese. Well done, Mr. Musk. Now, other interesting factoids. They drive their transistors to -5 volts to turn them off and to positive 20 volts to turn them on. What else have we got going on for you guys? Yeah, I'm going to talk a little bit about the current sensors. I'm going to do, that'll be in more detail in the next video, but just very, very briefly, the current sensors on this inverter work on two phases, so the two outer phase legs have got current sensors on them. And they'd be familiar to those of you that have worked on the small drive units from the SX, in that they are analog current sensors centered at 2.5 volts. So we'll be working out, you know, what the, whatever they call it, you know, how many millivolts per amp that they deflect when we run some current through this thing. But in the meantime, the big kind of a first step is getting the power stage under our jurisdiction, which we have done. So I'm going to get rid of me for you now, and I'm going to just use the, I've got another computer going on here, where I've got the analog discovery connected to it, and you'll see here I've just got some little 12 volt lamps here. So hopefully you're going to be able to see at least a few of them working. There's another one hiding over here. I'll try and bring it into shot for you. So I've just got a couple of little 12 volt lights. So at the minute, our shutdown pins are all pulled up to 3.3 volts. I've got the, it would be the phase B low side switch turned on. And I am now turning on the phase A high side switch. Hopefully you'll be able to see we've got some, let me turn off that overhead light, and you'll be able to see there that we've got some lights going on. So let me show you that again. So I've just got the 3 lamps rigged up there, as you would typically see for a delta connected 3-phase motor. So we can turn off that one. We can turn on another one there. We can't turn on both on the same phase. So again, we can, you know, we can pretty much mess about here with phase sequencing without harming anything, which is, you know, pretty impressive considering the fact that, you know, prior to this you could pretty much blow up your inverter just by sending it, as I say, the wrong signal. So this is, as I say, about the height of the excitement for you today, guys. We can flash a couple of 12-volt filament lamps. But main thing is that we have control of the power stage, and our next operation with the inverter here now will be to get us to the point that we can basically will be to get us to the point where we can basically run a three-phase motor, just a little induction motor here on the bench. So that's about it. That is what we've got for you on our, as I say, kind of a first milestone video on our Model 3 inverter reverse engineering. So I do hope that you have enjoyed this. I hope you're enjoying this particular series too. We've a lot of Model 3 hardware to get through, but you know, baby steps, right? So that's about it, folks. Do not forget to dislike, unshare, do not subscribe to this crap. We will see you in the next episode. I'll put some links in the description. It'll be the usual suspects, Open Inverter Forum and GitHub for all the various open source projects and discussion and support forums, Patreon and PayPal should you wish to financially support me in this crazy crusade, and whatever else I can think to put in there that will bore you to death. So until then, happy silicon carbide Mosfet driving.